Now that we've learned what the polar coordinate system is, we want to actually talk about how to produce polar graphs. So we're going to spend some time talking about how to exploit symmetry. We'll look for the zeros, the maxima on some of these graphs, and then we'll look at different examples of different types of polar graphs. So part of what we'll do today will be some actual computational type work, and part of it will just be looking at different types, discovering their different traits, seeing how the equation relates to the graph, and so on. The first part of what we're going to do today is more calculations based, and the end of this particular lecture is more just informational. Let's go ahead and get started. I'll share my screen with you so that you can see more easily my notes. Now that I've shared my screen with you, I want to draw your attention to what we want to do today, which is producing polar graphs. We are going to exploit them for symmetry. We'll talk about plotting points. Now, again, I don't typically expect my students to plot points to graph a polar graph. I typically allow them to use technology. We'll also, however, talk about finding the maximum on a polar curve, and also how to find zeros on a polar curve and what zeros are on a polar curve. We're going to start by reviewing what we talked about in the last video about symmetry. So remember, a polar equation describes a relationship between R and theta on a polar grid, where the polar grid looks like a series of concentric circles, where the center is called the pole and corresponds to the origin on the XY rectangular coordinate system. R is a measure from the pole, or the origin, out to a point as if measured along the radius of a circle. Theta, on the other hand, is measured counterclockwise from the polar axis, which is the positive x-axis, in a counterclockwise rotation. If we go clockwise, then theta would be negative. Remember that we write the ordered pair r comma theta, which is backwards to what we do in rectangular coordinates. We give the dependent variable r first and the independent variable theta second. This is, of course, how we graph in polar coordinate systems. Symmetry is just something to help us recognize and plot points when we're looking at an equation. There are, of course, three basic types of symmetry when we're talking about graphing. And they're the same three types of symmetry we have in the rectangular coordinate system. We have x-axis symmetry. That's when you fold it over the x-axis and the graph lays on top of itself. We have y-axis symmetry, which is when you fold the graph on the y-axis and it lays on top of itself. And then we have origin symmetry, which is when we fold the graph twice, once on the x-axis, once on the y-axis, and it lays on top of itself. Now, for in the polar coordinate system, we don't always talk about the x and y axis. So what do we talk about? Well, the x-axis just becomes that theta equals 0 pi line, which goes through the pole and extends to the left and the right. It is the same as the x-axis. And when we talk about the y-axis, we're talking about the line that goes through theta equal pi over 2 going in the positive y direction, and theta equal 3 pi over 2 going in the negative y direction. So we can talk about the same thing. When we talk about origin symmetry in the polar coordinate system, instead of calling it origin symmetry, we can call it symmetry with respect to the pole, since the pole, of course, is the origin. So failing symmetry does not necessarily mean that the graph doesn't have symmetry. Lots of graphs that are in the polar coordinate system have symmetry of a type, but not one of those three. So not symmetry along the 0 pi line, or along the pi over 2, 3 pi over 2 line, or symmetry with respect to the pole. They have a different type of symmetry. And let me draw an example of one for you right now that would have that kind of symmetry. So we have different concentric circles, and I drew the XY coordinate system just to make it easier for you to see what I was doing. And let's suppose, now you're going to have to use your imagination because I'm not great at drawing. Let's suppose we have something that looks like this in the polar coordinate system. Well, now it doesn't have symmetry to the theta pi line. And of course, theta equals 0, theta equal pi line. This is theta equals 0, and this is theta equal pi. And then coming up this way would be theta equal pi divided by 2. And coming down here, we have theta equal 3 pi divided by 2. So it doesn't have symmetry along the 0 pi line or the pi over 2, 3 pi over 2 line. And if I folded it twice on those, it's not going to lay on top of itself. But it does still have symmetry to itself. In fact, and this one has symmetry across the identity function. So it's got symmetry to itself across that particular line, which is just y equal x. So it is possible for the polar graph to have symmetry that doesn't correspond to one of the three major types. We're going to primarily focus on those three major types and figure out how we can find the three different types. Let's now talk about symmetry about the x-axis. The x-axis is also called the theta equals 0 to theta equal pi line. All right, so we have this line that extends theta equals 0 going off to the right, theta equal pi going off to the left. It's just another name for the x-axis. If it is symmetric across that, then it turns out that if we have an angle of theta, and then we take another angle, which is actually negative theta, but has the reference angle of theta, this is what creates that symmetry across the x-axis. So we can test for symmetry across the x-axis by replacing theta with negative theta. Now, you also have to think about your trig functions. And remember that when we have cosine of negative theta, that this becomes cosine of theta. In other words, the cosine function does have this particular behavior in a polar equation. Cosine of negative theta is cosine of theta. That does not work, however, for sine. Sine of negative theta is equal to negative sine of theta, so that would change the trig function. But we can see that if we were graphing with cosine in a polar equation, that replacing theta with negative theta would give us back the same exact expression. It wouldn't change it. So it's likely that it might have this kind of symmetry across the theta equals 0 to theta equal pi line. And that should be a 0 right there. Don't know how I got theta in addition to theta equal theta line. Okay, so this is the first type of symmetry we're talking about. And again, this means that if r theta is on the graph, then r negative theta is on the graph, or r negative r pi minus theta is also on the graph. It lays on top of itself. If you fold it on the x-axis, which is that theta equals 0, theta equal pi line. And an example of this is something called a limacon, 3 plus 4 cosine theta equal to r. And you can see right here that it definitely does have that relationship. So we'd call this angle right here theta, and we'd call this angle right here negative theta, all right? Now, why does it have that relationship? If we look up here to the equation, remember that the cosine of negative an angle is the same as the cosine of the angle. So replacing theta with negative theta doesn't change the equation. And because it's exactly the same equation, that tells us that it has x-axis symmetry. What about the second type of symmetry, which is symmetry about the y-axis? Now, the y-axis, of course, is going to be that theta equal pi over 2 to theta equal 3 pi over 2 line. All right, so this is the pi over 2 line here, and this is the 3 pi over 2 line down there. And so we're talking basically about the y-axis again. But remember that theta goes off only in that one direction. So pi over 2 goes up like the positive y-axis, and theta equal 3 pi over 2 goes down like the negative y-axis. So when we're looking at these, when do we have symmetry across the y-axis? Well, when we're looking at these, notice that it works as long as the reference angle for both of these is the same, similar to what we saw last time, but last time it ended up being theta and negative theta. This is not negative theta. Negative theta is down here, and that's what we're not we're talking about. This angle right here is theta, and the other angle that we're talking about is this angle right here, which is actually pi minus theta. In other words, it's what's left if we were to come all the way around. This would be pi, and its reference angle is theta, so it's all of pi minus this reference angle, which is theta. So to determine if we have y-axis symmetry, then we're going to replace theta with pi minus theta, which is the supplementary angle. Now, which function do we know comes out to be the same? Well, if we're thinking about these right here, whenever we have pi minus theta, this would be quadrants 1 and 2, or it could be 3 and 4. So when we're looking at this, notice that sine is going to have the same value because sine is positive in quadrants 1 and quadrant 2. So it turns out that the sine of pi minus theta is equal to the sine of theta. But that means that sine must have y-axis symmetry on a polar graph. Now, cosine, on the other hand, does not. So when we do cosine of pi minus theta, we don't get cosine of theta. We instead get the opposite of cosine of theta. In other words, it changes the sign of it. So this would end up being something different. So when we replace theta with pi minus theta, we don't get the same value. We get the opposite of the value. So cosine does not have this kind of symmetry across the pi over 2 to 3 pi over 2 line, but sine does. So let's take a look now. Again, if r theta is on the graph, then r pi minus theta is on the graph, or negative r negative theta is also on the graph. We'll look at another limacon. This is 1 plus 2 sine of theta. And again, remember that sine theta does have this y-axis. I know it's different from the rectangular, right? It's total opposite, because in the rectangular system, cosine has y-axis symmetry and sine has origin symmetry. So this is totally different. We have to kind of switch gears and think about polar. So when we're looking at this, this is a limacon again, and we can tell that we've got these two angles right here, and they turn out to have exactly the same value of sine because one's in quadrant 1, one's in quadrant 2, but they have the same reference angle. And so it does have y-axis symmetry. Now, the third type of symmetry would be symmetry about the origin, which is also called the pole. All right, so about the pole. So this is our third type. And just as we had with rectangular systems, if it has two types of symmetry, then it has to have all three. So it's not possible to have precisely two. It either has no symmetry with respect to those three things, or it has one type of symmetry, or it has all three. You cannot have two types. So when we talk about this one is a little bit more difficult because the typical way of talking about it is to replace r with negative r, and that doesn't change the equation. So that would happen whenever you have something like r squared. If you replace r with negative r, when you square it, you're still going to get the same thing. So that would definitely have this symmetry about the pole. But we can also, because of the way that we define negative r, meaning that if we have a negative radius, we come out along that 180-degree line, we can also think of it, instead of replacing r with negative r, we can think of it as replacing theta with either theta minus pi or theta plus pi. All right, so then we're coming out across over here. Now, sine is positive here and negative here. So sine does not naturally have symmetry about the pole. Cosine is also positive here and negative here. So it is not going to naturally have symmetry about the pole, neither sine nor cosine. So what could force those to have symmetry about the pole? Well, if you square sine or you square cosine or raise them to any even power, then you'll get the same number. And because you're squaring it, the signs will be different. But when you square or raise to an even power, they'll become the same. So that can also lead to symmetry about the pole. So if R theta is on the graph, then negative R theta is on the graph, and R theta minus pi or R theta plus pi is also on the graph. All right. So when we're looking at these, here's an example of one. This is called a Limnus Gate, which has that figure 8 pattern. And you can tell from the equation you have R squared. So when you replace R with negative R, you clearly get the same thing, and you get this sort of graph right here. All right. And we're going to see another one in just a moment, which is going to be slightly different. We're going to have to do some work to prove that that one has symmetry about the pole. Okay. Now, the next thing we want to look at is this problem right here. We want to test for symmetry. So we see that we have cosine. So again, there are 3 types of symmetry that we want to look at. We're going to think about replace theta with negative theta. That's one type. The second type would be to replace theta with pi minus theta. That's the y-axis symmetry. And the third one, we're going to talk about replacing theta with theta plus pi or theta minus pi. Or R with negative R. This third type, there are more than one way to check it, all right? And you need to know both, because sometimes you can do one and you can't do the other, and sometimes it's vice versa. You can do the other and not the first. Okay, so these are our 3 different ways of checking. So the first thing I'm going to do is I'm going to check type number 1, and I have R equal -2 cosine, and I'm going to replace theta with negative theta. But the cosine of negative theta turns out to be, because on the rectangular system, you know, the cosine, it does have y-axis symmetry. You know, on polar, it just makes it different. This becomes -2 cosine of theta, which was the original problem. So it has x-axis symmetry. All right. Now, what about the next 2? We know already, because it's cosine, that it does not have symmetry of the supplementary angle. So part 2 would be no. All right. So we have R equal -2 cosine of pi minus theta is going to give us a -2 cosine of theta, which is going to give us a +2 cosine theta. It's not the original equation, so no y-axis symmetry. Right? And then the last one that we're going to look at, of course, is going to be replacing theta with theta plus pi. So we have -2 cosine of theta plus pi, but this is going to move it from quadrant 1 to quadrant 3, or quadrant 2 to quadrant 4, or 3 to 1, or 4 to 2, where cosine changes sign. So this is going to also be 2 cosine of theta, which is different. And so it does not have symmetry about the pole, right? So the only kind of symmetry we see here is the x-axis symmetry. All right. Now let's go ahead and take a look at the graph. Now, obviously, the easiest way to do this is just to graph it. Now, I did this algebraically using trigonometry, but here's the graph right here, and here's a link if you want to play with the graph. And it's obvious once you graph it what the symmetry is. It's going to fold this way, all right? And again, that's because replacing theta with negative theta does not change the equation. It gives you the same equation back again. Okay, let's look at example number 2. We have test the equation for symmetry, R equal 3 minus 3 cosine of theta. So when we're looking at this one, again, we can see that we've got cosine. So we know that theta being replaced by negative theta is not going to change the equation. So we definitely, oops, I lost my 1. We definitely have x-axis symmetry. That's for sure. All right. Then replacing theta with pi minus theta, that is going to move it from quadrant 1 to quadrant 2, or from quadrant 2 to quadrant 1, but cosine has different signs there, so definitely it does not have that symmetry. So we have no y-axis symmetry. And the last one, replacing theta with theta plus pi or theta minus pi, moves it from quadrant 1 to quadrant 3 or 2 to 4 or vice versa. And again, it's going to change the sign of cosine, which is going to change it from 3 minus 3 cosine of theta to 3 plus 3 cosine of theta, which is not the original one. So again, we see that we have no symmetry about the pole. Right? And we're doing this using our knowledge of what happens with cosine when we replace theta with negative theta, or replace theta with a supplementary angle, or replace theta with something 180 degrees around. Now what we want to look at here is this graph. This is called a cardioid. It is actually a type of limacon, so it is also a limacon. Limacon is the broader group. Cardioid is more specific. When these two values are the same in a limacon equation, it produces a cardioid. And cardioid got its name from, well, cardiovascular, heart, basically. It's kind of a heart shape, except it's more round down here at the bottom than we typically call a heart shape. But it does have x-axis symmetry, or symmetry along the line that extends from theta equal 0 to theta equal pi. Now we want to take a look at the next example, which is example number 3. This one is sine. So when we look at sine, we're going to have a slightly different result, right? Remember, for sine, if you replace theta with negative theta, you get negative sine of theta. So if I do this one, I get r equal 3 plus 2 sine of negative theta. And this becomes 3 minus 2 sine of theta. But that is not the original equation we have. So we have no x-axis symmetry. Then we can check with the supplementary angle, but it turns out that sine has the same value as its supplementary angle. Oops, forgot my minus there. So this turns out to be 3 plus 2 sine of theta again, which is the same as the original equation. So we do have y-axis symmetry. Now, when we replace theta with theta plus pi, we're switching all the way across into the opposite quadrant. So that means that we go from 1 to 3 or 3 to 1, or 2 to 4 or 4 to 1 plus pi, right? And when we do that, this is going to give us 3 minus 2, the sine of theta, which is not the original. So we have no symmetry about the pole. So this one only has y-axis symmetry, which will be along that pi over 2, 3 pi over 2 line. Now let's look at the graph of it so you can see what it looks like. This is also a limacon. It is not a cardioid because these values are not the same, but it is a limacon. Instead of having a loop in it, it's got more of a dimple, all right? So that happens sometimes. So we've got more of a dimple, sort of like a dent, an indentation in it. And it definitely does have y-axis symmetry, or symmetry along this pi over 2, 3 pi over 2 line. Let's take a look now at example 4. Example 4 is slightly different than the ones that we've been doing. It does not have a trig function. So it doesn't have sine and it doesn't have cosine. So let's just imagine what would happen if we did all of these. So if I replace theta with negative theta, I get 2 over negative theta, but that's not the original equation. The original equation is 2 divided by theta. So no symmetry here. And what about the second one? Well, I can replace theta with pi minus theta, but again, pi minus theta switches from one to another. So it's no longer in the same quadrant. It's not the same angle. It's not going to give me the same value. So no symmetry here. So no y-axis symmetry. Now the last one that we have, remember we said we could test it 2 ways. You can either test by replacing theta with theta plus pi or theta minus pi, or you could replace R with negative R. And in this case, it's not going to give you the same thing. I think most of the time it's safer to replace theta with theta plus pi or theta minus pi. And again, those are clearly not the same angle. They may have the same reference angle, but they're not the same angle. So because this isn't in a trig function, it's going to be a different value. And that means it does not have symmetry about the pole. So this is a graph that has none of these major three types of symmetry. So no symmetry about the pole. All right. And when we produce this graph, it actually looks like this. It's a kind of a spiral. So we have this spiral going on. There is a pattern to it. There's clearly, I mean, it's a spiral, so we can see that it's a spiral, but it doesn't have the three types of symmetry. If I fold on the x-axis, this doesn't lay on anything. And that's not going to lay, there's nothing down here exactly at the same distance for it to lay on. So there's no x-axis symmetry. Same thing for y-axis. This part right here isn't repeated over here. So no y-axis symmetry. And that leaves pole symmetry. Symmetry about the pole, we'd fold twice, but again, there's nothing for it to lay on top of. So it does not have any symmetry at all. We have one more example to do, which is this one right here. And what I'd like for you to do is go ahead and pause the video, work out the types of symmetry, and then turn the video back on and we'll compare our answers. So hopefully you found at least the first two did exist, that it does have both x-axis symmetry and y-axis symmetry. Remember, replacing theta with negative theta does not affect cosine, so it ends up being exactly the same. So definitely we have x. On the y, or y-axis symmetry, we replace theta with pi minus theta, the supplementary angle. And when we do that, it does affect cosine. It changes the sign. They have the same reference angle, but they're in adjacent quadrants, so they have opposite sign. So that gives me negative cosine of theta, but it's squared. And when I square the negative, it goes away. So I again get the original. And because I have two types of symmetry, I must have all three. Now, interestingly, on this problem, checking the result with replacing theta with theta plus pi, again, this puts it in the opposite quadrant, not adjacent, but the opposite. So 1 to 3 or 2 to 4. And that will change the sign of the cosine, but because it's squared, you end up with the same equation. But on this particular example, replacing r with negative r does not work. It looks like it gives you something different. But because of the way that the cosine is oriented, being squared, and the r being the negative shooting out on that 180-degree line, it actually turns out the same. So replacing r with negative r doesn't work to check this particular one. You need to use the other method. So this one should have x-axis symmetry, y-axis symmetry, and when you fold it twice, it should lay on top of itself. And it does. This one also has a particular name. I'm trying to remember what it's called. I think a Hippopede is what it's called. It basically, it's two circles side by side touching at one point. And we can see that it definitely has x-axis symmetry, but it also has y-axis symmetry. And if we fold it twice, it will lay on top of itself. So it also has symmetry with respect to the pole. So I hope that you now have a better feel for how to use symmetry to help predict sort of the basic shape of a polar graph. What we're going to turn our attention to now, after having looked at symmetry, is we're going to look at graphing and then at zeros. So what is a zero? First, we want to talk briefly about graphing polar curves by hand. Now, we will graph two by hand in this particular video, but again, my students, I do not expect you to graph by hand. So what I will have you do instead is use a graphing calculator or technology. So we enter values of theta into a polar equation and we calculate r. So steps to graphing the polar curves by hand, you need to make an R Theta table. Remember, that's the normal order for the polar coordinate system, dependent, then independent. We'll use angles with reference angles that correspond to our favorite 5 angles. That's pi over 6, pi over 4, pi over 3, pi over 2, and 0. So we'll use the ones that relate to those. We'll plot the points, connect the points smoothly. Don't be like a 4-year-old and draw a zigzag picture trying to connect the dots. We want smooth, curvy things. And then be aware that the curve could retrace a path or intersect itself, so it could cross itself up. And we can use symmetry to help. So when you're creating an R Theta table, it looks something like this. And again, you start with our favorite 5, and then you'll move into quadrant 2. Your next angle would be 2 pi over 3, and then 3 pi over 4, 5 pi over 6, and pi. And then you keep going 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, etc., all the way around the ones that have these as the reference angles. So most of the time, we're going to rely on Desmos to do our graphing, but we will do 2 examples today where we graph by hand, just so you can get a feel for what it's like. Just in case some future professor requires you to graph by hand or plot by hand. Let's take a look now at finding zeros on the polar curve. So what are zeros on the polar curve? This actually turns out to be a pretty important skill for Cal 2 and Cal 3. We're often looking for zeros of the curve. And zeros of the curve are different than what we define them to be in the rectangular system. In the rectangular system, a 0 is where it crosses the x-axis. In the polar system, a 0 is where it crosses the pole. So it's when r is equal to 0. So a 0 of the polar curve is whenever it intersects or crosses the pole. So it's going to hit the pole, also called the origin. All right, so this is different than what we had in the rectangular coordinate system. So basically what we do is we take the equation, we set it equal to 0, and we try to find the angle or angles, theta, that cause it to hit the pole. Remember that it can intersect the pole multiple times. So here's an example of one. This is number 6, r equal 3 cosine of theta. And we want to find where it hits the pole at what angles without converting this back to rectangular. We want to be able to stay in polar coordinates. So to find the zeros, we set the equation r equal to 0. So we have 3 cosine theta equals 0. Then we divide both sides by 3. So we get the cosine of theta is 0. Now the cosine of theta is 0 at 2 places on the unit circle. And that would be at pi over 2 and 3 pi over 2. But of course, if we keep going around, then it has all the multiples of pi over 2 and 3 pi over 2. So we write that as pi over 2 plus n pi, any pi multiple of pi over 2 or 3 pi over 2. And it will intersect itself infinitely often. Let's take a quick look at what this curve looks like. Here's the link down here at the bottom. So we're going to click on that. And you can see that it basically gives you a circle. All right. So if you want to know where it is, then it's going to intersect the pole here at this particular point. So it's going to intersect more than once if we go from 0 to 2 pi. Now, this is where the graphing calculator has a bit of an advantage in that you can actually watch it come around and hit it more than once if you use that -0 symbol or the key symbol in order to make it graph. And you can see it hit the pole multiple times, right? Right. Let's take a look now at finding maxima on polar curves. We can also talk about minima, but minima don't mean as much on a polar curve because if the radius is negative, we just shoot out on the 180-degree line into the opposite quadrant. So we really only talk about maxima on polar curves. So this can also help us to visualize the curve and graph it. when we're looking for maxima, at least in this class, we're primarily going to be dealing with sine and cosine. Why? Because of the 6 trig functions, those are the only 2 that have a maximum. The others don't have maximums. They go off to infinity, right? Think about the graph of cotangent or tangent. They have asymptotes, but they extend to infinity, and so do secant and cosecant. But the graphs of sine and cosine definitely do have both maximum and minimum values. They're both between -1 and 1. So their minimum value is -1 and their maximum value is 1. So if we get a radius of either 1 or -1, if it's -1, we just shoot out on the 180-degree line. And this will give us a maximum value on the polar curve. So again, maximum for sine, of course, is going to be wherever it's 1 or -1. So it's going to be at multiples of pi over 2 or multiples of 3 pi over 2. So again, we can say multiples of pi over 2 plus n pi. Again, that's because if it came out to be a -1, we would just shoot out 180 degrees in the opposite direction and it would still have that length. All right. So basically, sine has maximums along that pi over 2, 3 pi over 2 line. What about cosine? Cosine reaches its maximum and minimum values on the rectangular coordinate system at multiples of 0 and pi. 0 and 0 and pi. So it reaches a -1 at pi and it reaches 1 at 0 or multiples of 2 pi, however you want to write it. So again, when it's along that line, either at 0 or pi, if it's at pi and it's a -1, it's simply going to shoot out in this direction, but it's still going to have the maximum possible length. All right, so we'll have multiples of 0 or 2 pi or pi. Okay, so let's find the maximum of this particular equation, 3 cosine of theta, but without converting to rectangular coordinates. Now, there are different ways of thinking about this, but the simplest way of thinking about it is just looking at the equation and going, what would make r the largest possible value? Well, if cosine of theta is 1, then this would become 3. So then I'm looking for the angle where the cosine becomes 1, which would be at 0 or 2 pi or any multiple of that. Now, what if it were pi, which would give us -3 because cosine of pi is -1? Well, then I wouldn't graph it in the pi direction. I would shoot out and I would still graph it in the theta equals 0 direction. So it would shoot out in the opposite direction. But again, it would have a maximum value of 3. So it would come out towards the right, right? So that gives us basically what we're looking at there. And I believe this is the one that we did up here, 3 cosine of theta. Did we use that? There it is, 3 cosine of theta. So this is this graph right here. And where does it reach its maximum value for r? Again, we're not talking about maximum value for y. We're talking about maximum value for r. Where is it the furthest away from the pole? And that would be right here at 3. And again, if you got -3, we wouldn't graph it in that direction because r is negative. We would shoot out and still graph it to the right. Okay, let's take a look now at the next one. So we did example 7. Let's take a look at example 8. Now on example 8, we want to explore symmetry, find the zeros, find the maxima, and create an R theta table and plot r equals 4 sine of theta. So the first thing that I would like you to do is to go ahead and evaluate the symmetry. So let's do the symmetry right here. Remember, we have 3 different types of symmetry. So we're going to replace theta with negative theta, and that gives us x-axis symmetry. And we know that in this case, that's not going to work because this would give me 4 sine of negative theta becomes -4 sine of theta. That's not the original equation, so no, we do not have x-axis symmetry. Checking the second one, we're going to replace theta with the supplementary angle pi minus theta, but in this case, it does work for sine. So we have r equal 4 sine of pi minus theta, which turns out to be the same as 4 sine of theta. So it's exactly the same equation. So we do have y-axis symmetry. All right. Now, do we really need to check the last one? We could check the last one, but notice that I know this one does not exist and this one does. Remember that I said for symmetry, you either have no symmetry, precisely one type, or all three. It's not possible to have all three because this one doesn't exist and this one does, which means that I can't have the third type. So you can simply do that right away. No symmetry about the pole because of the rule for all three. All right? Or you could check by replacing theta with theta plus pi. All right? Okay. And you will see that it gives you -4 sine of theta. Okay. So we checked the symmetry. We're expecting to see some y-axis symmetry here. Zeros, where would I find zeros? When would it come around and hit the pole? So let me shrink this up just a little bit here. I'm going to move that down. All right, so when would it hit the pole? What is the largest possible value for, or that's maxima? When would it hit 0? When would this be 0? So if we're looking for zeros, this is going to be r equals 0, which implies that 4 sine of theta equals 0, which implies that sine of theta equals 0. So this is going to happen whenever theta is 0 or pi or multiples of those two. So I'm expecting that when the angle gets around to being 0 or pi, that it hits the pole. So it's going to come to the pole at those 2 points. So what I have here is I have the ordered pair 0, 0, and I have the ordered pair 0, pi. The radius is 0 when the angle is 0. The radius is 0 when the angle is pi. So I have those two as well. And then I want to find maxima. So to find maxima, my equation is r equal 4 sine of theta. And when I'm looking for maxima, I'm looking for the extreme values of r. So this would be when r is going to be either as small as possible or as large as possible. As small as possible is just going to graph in the 180-degree line. So sine reaches a maximum at pi over 2 when it is 1. So the maximum value is going to be 4, and that's going to happen at pi over 2. So when I reach pi over 2 on the angle, the major length should be 4. Now, what happens if this becomes 3 pi over 2? Then this becomes a -1, and this becomes a -4. But that's going to make it shoot out in the opposite direction along the pi over 2 line, also at length 4. So it essentially plots the same point. So I can plot both of those points right there, right? And then I know it's going to hit the pole twice. It hits the pole when theta equals 0. It hits the pole when theta equals pi. And I know it's got symmetry. So I've got a little bit, but not a lot. Now we can go ahead and fill out the table. So you may want to pause the video, fill out the table, and then turn the video back on and we'll compare our points. So let's take a look at what you got and what the patterns are that are developing when we plot points. So again, what you do, of course, is you just plug it into the equation that we see here. And let me turn off my paragraph markings so that it's a little bit more clear. There we go, into the equation 4 sine of theta. Well, the sine of 0 is 0, so 4 times 0 is 0. So I get the ordered pair 0, 0. The radius is 0 when the angle is 0. When I plug in pi over 6, I get 4 times the sine of pi over 6. Sine of pi over 6 is a half, so I get 2. So this gives me the ordered pair 2 comma pi over 6, and so on as you come down here. Now notice down here, when I have 7 pi over 6, the sine of 7 pi over 6 gives me the same thing as the sine of pi over 6, but with a negative number. So this is also going to give me a 2, but a negative 2. Now, because of the way the negative radius is defined, this is actually going to plot on the 180-degree opposite quadrant. So instead of on 7 pi over 6, it's going to plot on the pi over 6 line. And instead of negative 2, it'll plot 2, which is the same point we got up here. Now what you do is you simply take those points and you plot them up here on the unit circle. So on the pi over 6 line, we plot 2. On the pi over 4 line, we plot about 2.8. On the pi over 3 line, we plot about 3.5. And then we see it's got symmetry across the y-axis, so we can come back down. And we basically end up with a circular pattern with a radius of 2. The diameter is 4, but the radius is 2. And it touches the pole at the bottom. And if we were to plot this, we would see that that is, in fact, exactly what we have. So we have done it correctly. Let's now take a look at the next problem. In the next problem, we're essentially doing the same thing again. But on this problem, we're looking at the equation 5 minus 5 sine of theta. And we want to graph this one by exploring symmetry, finding zeros and maxima, and creating an R theta table. So we're going to skip doing the R theta table, but we will take a look at the symmetry. So we're going to look at the symmetry, then we'll look at finding zeros and the maxima. So when we're looking at those, what are we going to get when we look at those particular values? So let's see, add that right there. Okay, so if we're exploring symmetry, remember there are 3 basic types. You're going to, oops, for some reason it's not plotting. Replace theta with negative theta. That gives us x-axis symmetry. But sine of negative theta is negative sine of theta. So this would lead us to have 5 minus 5 sine of negative theta becoming 5 plus 5 sine of theta, which is not the same. So we have no x-axis symmetry. All right. And then when we're looking at the next one, if we wanted to explore the y-axis symmetry, then we simply replace theta with pi minus theta, the supplementary angle. But this moves it into the quadrant adjacent to it. And quadrants 1 and 2, sine is both positive. So since they have the same reference angle, you get exactly the same value. So R is equal to 5 minus 5 sine of pi minus theta, which turns out to be exactly 5 minus 5 sine of theta, which is the same. So we know that it has y-axis symmetry, right? Now, because we have no x-axis and we do have y-axis, we can't have symmetry about the pole because we either have 0 types, 1 type, or all 3. So we have no symmetry about the pole. All right. Now, the next thing we want to talk about is maybe finding the zeros. So when we're looking at the zeros, this is when R is equal to 0. So solving this equation, we get 5 minus 5 sine theta equals 0, which means that we have 5 equal 5 sine theta, which basically means that we have sine theta equal 1. And this is going to happen when theta is equal to pi over 2. All right. So we're going to have it hit the pole when theta is pi over 2. And that's the only one that we found for that particular expression. Now we want to take a look at the last thing, which is exploring and exploiting maxima. So when we look at it exploiting maxima, we'll create a little shape over here to put our work in. So when we're looking at maxima, again, what we're looking at is what would cause R to be the maximum value that it could be or the minimum value that it could be? What would be the largest? What would be the smallest? And for that, you typically want to look at the maximum and minimum for sine. If sine turned out to be a +1, then this is going to become 0, right? Because I would get 5 minus 5. So R would be 0, right? So I know that when theta is equal to pi over 2, R is 0, but I already found that. That was my 0 value over here. And we can write down that ordered pair, 0 pi over 2, right? Now, let's think about doing something different then. What if I allowed theta to be 3 pi over 2, which is the other extrema value for sine? That would give me a -1, but -1 times -5 would make it a +5, and 5 plus 5 would make it 10. And that seems to indicate that that would be the largest possible value I can get. So R equals 10 when theta is equal to 3 pi over 2, right? And otherwise, whatever the value is, it's going to vary then. Sine of theta is going to end up being like something between 0 and 1 or 0 and -1. So it's going to vary. So if this came out to be, say, pi over 6, this would become 1/2. So we have 5 minus 5 halves, which would give us 5 halves, all right? So it looks to me like it's going to vary between 0 and 10, where 0 is the smallest found here, and 10 is the maximum. So we have the ordered pair 10, 3 pi over 2, right? Now, the next thing we would do is create an R theta table, and then we would plot the points that we have found through there onto the graph. Now, I don't want to take the time to plot the points, but if you want to, go ahead and pause the video, plot the points by hand, and then turn the video back on, and we'll compare what we get when we plot this one on Desmos. So 5 minus 5 sine theta. Right? And I get this graph right here, which is in fact a cardioid. It's also a limnus gate. Limnus gate is the broader category, but because these are both 5, it turns out to be a cardioid. So it has that sort of heart shape again. Notice that it is hitting here at 0 pi over 2. And you may go, well, why isn't that 0, 0? Well, if you look at the angle that it's sweeping around, do you see how it's approaching here from the angle of pi over 2? So that's actually 0 pi over 2. And when it comes down here, we have that other angle down here, which is going to put us down here at 10. All right. So when we're looking at this one, we have a distance of 10 at 3 pi over 2, which we got right here. Didn't finish drawing that. And then we have 0 at pi over 2. So we got both of those points. And it does have y-axis symmetry that you see here. Okay, now we want to switch gears a little bit. We've done our calculations work. And what we want to do now is we basically want to switch and we want to start talking about polar coordinates. In other words, let's start playing and having some fun with these really cool and exciting polar graphs. So let's start with limacons. The word limaçon is Old French for snail, which is a name that describes the shape of the graph. There are one-loop limacons and two-loop limacons, or inner-loop limacons, which are sort of my favorites. One-loop limacons are sometimes referred to as dimpled limacons when the ratio between A and B is between 1 and 2. So that's A divided by B. Now, here are the formulas for limacons that you can see right down here. So you have A plus or minus B sine theta and A plus or minus B cosine theta. So when the ratio of A divided by B is between 1 and 2, you get that dimpled pattern. And we saw a dimpled one up here. I'm trying to remember. Yes, it was this one right here. And so again, this is what we mean by a dimple. It's sort of an indentation in the graph. All right. So The other thing that you can get is an inner loop. And we've seen one or two of these as well. Now, what happens with the inner loop? When the magnitude of A is less than the magnitude of B, then you get an inner loop. Now, this is going to give you something slightly different. So again, the magnitude of A smaller than the magnitude of B, that would be like the constant out front less than the coefficient of the trig function. Then in that case, you're going to get an inner loop, all right? So, but again, notice that the ratio of A divided by B is 1/2, which is not between 1 and 2. That's why it doesn't give us the indentation. So this gives us an inner loop. And notice that this one has sine here, and that sine is associated with the y-axis, and this is what I'd call a vertically oriented limacon. And notice that it reaches its maximum when theta is equal to 3 pi over 2, because that gives us -1 times -2, which gives us +2 plus 1, which is 3. So it's hitting down here at 3 pi over 2. Right? That's the coordinates of that point in the polar coordinate system. Let's take a look now at another limacon. The inner loop limacon was discovered, at least most recently, by the German artist Albrecht Dürer, and he'd drawn lots and lots of things, and he found a method for drawing these inner loop limacons. He wrote a book about it. And then Blaise Pascal discovered it again. Etienne Pascal, the father of Blaise Pascal, he rediscovered it sometime in the late 16th century, 17th century. So here are different limacons. These are all inner loop limacons. So we know that the magnitude of A is less than the magnitude of B, and A divided by B doesn't fit between 1 and 2. So when we're looking at that, notice that the ones that have cosine in them are oriented horizontally, and the ones that have sine in them are oriented vertically. And not only that, but the one that has sine with a negative B is below the pole, and the one that has a positive B is mostly above the pole. And when we look at the pattern on these, we see a very similar thing. When we have plus B attached to cosine theta, the majority of it is to the right side of the pole on the positive side. And when we have minus B cosine of theta, the majority of the limacon is to the left of the pole on the negative side. All right. And here's another example of one where you get a dent or a dimple. And again, this is the ratio of A over B. And there's another way of writing that the magnitude of A is greater than the magnitude of B, but less than 2B. All right. And again, you can solve that for the ratio of A over B is between 1/2. All right. Between 1 and 2. Sorry, I put the two numbers together. So when we're looking at the next one, again, this gives us 5 over 3, which is greater than 1 and less than 2. So we know we have a dimple. Because it is sine, it's going to be oriented more vertically, which means it has that y-axis symmetry, and it's going to reach its maximum at 3 pi over 2, which is going to be a value of 8. And we also know, let's see, what else? I was going to mention one other thing, and it's gone. I've lost it. Oh, yes. Most of the limacon is below the pole because we have -3 sine of theta. Right? So here's another example of some dimpled limacons. And again, you see the same kind of pattern. If it's plus B cosine of theta, it's oriented horizontally with the majority to the right of the pole. If it's A minus B cosine of theta, then the majority is to the left of the pole. If it's A plus B sine of theta, it's vertical and the majority is above the pole. And if it's A minus B sine theta, the majority is below the pole and it's oriented vertically. Now, if the magnitude of A is greater than 2B, we get a sort of ovalish shape, and it doesn't have a dent or a dimple, but it does have a more flattened side. It's not circular. This side right here is flatter than it would be on a circle. So it's sort of an ovally shape with one side flattened out. All right, and this happens, of course, when you divide and you get a over b greater than 2. All right. Now let's talk about what lemniscates are. Lemniscates are a different kind of graph. These look mostly like figure 8s. Now the lemniscate always has symmetry to itself, but it may or may not have symmetry to the pole or to the x or y axis. It may, but it may not. It just depends. If it's tilted or rotated, it may not have symmetry in any of those respects. Tilted ones often have symmetry around the pole, but not always. Now, these formulas are distinct in that they generally feature r squared or r squared instead of just r. But you can also see them as r equal the square root of something. As long as you take theta around enough times, it's still going to graph the entire lemniscate. And we've seen one of these previously. All right, so let's take a look at a couple different ones that we have going on here. So here are some different lemniscates. This one right here is a squared cosine of 2 theta. And notice that it is symmetric with respect to the x-axis, which we would expect, because in cosine, replacing theta with negative theta doesn't change the value. The second one has symmetry with relation to the y-axis, and this is negative a squared cosine of 2 theta. And then this next one is a squared sine of 2 theta, which is rotated tilted. Notice that this one, when we multiplied by a negative, rotated it 90 degrees and made it symmetric about the y-axis. Now, these are both symmetric about the pole. If you fold twice, it will fold on top of itself. And this is with sine. So notice with sine, they get off kilter and going into quadrants 1 and 3 or 2 and 4. And with cosine, they stick on the axes. Now, sometimes the graphing calculators, when they plot these, you'll see that it kind of hangs out for a while and doesn't produce a graph. What happens is that occasionally the value that is underneath the radical may come up to be a negative value. And of course, the square root of a negative number is not real. It's imaginary. And because of that, it can't graph on the real graph. So it just sort of waits until theta spins back around into another quadrant where their value becomes positive again. All right, so that can happen when you're graphing on a graphing calculator. Desmos tends to graph them all at the same time, so you don't see that so much. Now, circles in polar coordinates are the absolute easiest graphs to graph. It's just r equal a constant where a is the radius of the circle, and that will center it at the pole. So if you write r equal 3, then you get circle of radius 3 centered at the pole. Now, what if you don't want it centered at the pole? If you want to center it along the pi over 2, 3 pi over 2 line, then you can center it at 0, a, r equal 2a sine of theta. Again, sine controlling vertical, so it plots on the y-axis. Or you can center it at a, 0 on the x-axis by using cosine, 2a cosine of theta, where a is the radius. 2a would be the diameter. So notice there's a difference here in these equations. A is the radius in both, but this has a coefficient of 2a, which is actually the diameter, and that just equals the radius. So when you're looking at an equation and you don't write it as 2a sine theta, 2a cosine theta, that coefficient becomes the diameter, all right? And the radius, of course, would be half of the magnitude of it. Now, here are some different circles that you can see right here. And I just graphed them all on the same graph because, well, it gets kind of tedious to do it one at a time and takes up a whole lot of paper. So r equal 2 is the one in green, and you can see it is centered at the pole. All right, and then the one that's in purple is 4 sine of theta. So we're expecting that the diameter here is 4, so the radius is 2, and it's going to be shifted up in the positive direction, and it's sine, so it's going to be vertical, so it's above the pole. And then -4 sine theta, again, should be vertical, but it should be mostly below the pole. And you can see it right here in black with radius of 2. And then r equal 9 cosine theta. Cosine is going to shift left or right. It's positive, so it's going to shift to the right. And again, 9 becomes the diameter, so the radius is 9/2. And it's centered over here at this point out here. And then you can shift it to the left by having -9 cosine of theta. All right. Now let's talk about Archimedean spirals. Archimedean spirals, the term A can be anything. Here's our formula right here, R equal A plus B theta. A can be any value. It can be positive, negative, and even 0. So it's okay to not have a constant there. And we've seen one of these earlier. Or something like it. The factor on B, however, that's multiplied by theta, that can't be 0. If that term is missing, then it ceases to be an Archimedean spiral. So it can be positive or negative, it just can't be 0. All right, then it won't be an Archimedean spiral. Now, what makes an Archimedean spiral different from the spiral we saw earlier? In the spiral we saw earlier, you notice how the spirals got wider and further apart as they continued to grow. This one, in an Archimedean spiral, the distance between each spiral is exactly the same, which is kind of wild. If you think about that, it must be very complicated to write down an equation for this in the rectangular coordinate system. I mean, how could you write an equation for something where the distance between each spiral is exactly the same as you go out? But again, it becomes very simple in polar coordinates. It just becomes A plus B theta. All right, and you'll see this one, which is 2 plus 3 theta equals R right there. All right, let's take a look at this one. Let's go ahead and open this one up just for fun. We can play with it a little bit and see what happens. So if I were talking about this one, I would say that it's kind of uncurling in a counterclockwise pattern, and it's going out here. Now this one is going from 0 to 12 pi. What would happen if I made the 2 a negative? Would that change it at all? It did. Let's take it back out and let's look at it again. So there's what it looks like. And you can tell that it's starting at the pole and then going into quadrant 1, then 2, and wrapping around that way. If I put a negative on the front, then it tends to be a tighter coil, but the distances are still the same. Now, if I take that off and go back to the original, what would happen if I replace that plus with a minus? So watch the graph. And now we have this. So instead of curling up and starting in quadrant 1, it's curling in a tighter pattern like this and coming all the way around. All right, so you can see that it's shifted. Let me duplicate this one. And we'll graph it in another color, and we'll put the plus on there so we can see the 2 at the same time. Right? And let's graph it in blue. Right? So now you can see the difference, what happens when you graph it. And it's kind of cool, right? It looks pretty cool. When you change this from a positive to a negative or vice versa. You can see that it's kind of starting at a different point and curling around. All right. So do I expect my students to memorize these equations? No, I don't. I don't expect you to memorize them. I expect you to kind of recognize it when you see it, but I don't expect you to memorize it. And there's another one right there. Now, for a very simple one of these in rectangular coordinates where A is actually 0, this is the equation that you would have to enter, all right? So this would graph a very simple one where A is 0. If A is not 0, it gets much, much more complicated. And this is, of course, why we like to do them in polar coordinates. Now, you can never completely draw the Archimedean spiral because the domain is negative infinity to infinity. But usually going 0 to 12 pi is enough to see what's happening. Let's look at logarithmic spirals, which are based on the Nautilus shell. Logarithmic spirals are not always covered in textbooks, but they're kind of fun, so I like to include them. They're sometimes called the Nautilus spiral because they resemble the chambers of a Nautilus shell. Notice how the chambers get larger as it moves out away from the center. And that's going to happen with a logarithmic spiral. The distance between the spirals gets bigger as it moves out. And the equation is r equal ab to the theta, where a cannot be 0, it can be negative, but it can't be 0. And b has to be just like the normal base to an exponential equation. It has to be strictly positive and not 1. When we do 1, it just becomes something much simpler. All right. So here are some examples of different logarithmic spirals, and you can see them growing like that. All right. Not just 1. Okay. So there's another one as well. Notice that when we made the base a number less than 1, that it became a much smaller spiral. All right. These up here were going around to 400 and 600 and so forth. And when I made the base be between 0 and 1, it became a much smaller, tighter spiral. All right. So just for fun, let's see what would happen if we made the base be 1. And go ahead and see if you can come up with a value. Yep, of course, it just gives you a circle. So 1 to any power is just going to be 1, and that's why you just get that. All right. I think I lost my to the theta power, but it's still just going to give you the circle of radius 1 centered at the pole. And that's why we don't allow the base to be 1. We've already talked about cardioids. They are a special case of limacons. Limacons, remember, are a plus or minus b sine theta. These are the equations for limacons. Cardioids happen when the a and the b are the same number. So that becomes a times 1 plus or minus cosine of theta, or a times 1 plus or minus sine of theta. All right, where a needs to be greater than 0. All right, so here are some cardioids. They're kind of heart shapes. They have a cusp right here. They do what you would expect they would do. When it's plus a cosine of theta, it's oriented horizontally and the majority is to the right of the pole. When it's minus, the majority is to the left of the pole. When it's sine, it's vertical. And if it's plus, then the majority is above the pole, and minus, the majority is below the pole, just like limacons. Now, I did the same thing here, but it's a little bit harder to see these when you're looking at these. So let's open it up on Desmos. And what I'm going to do is I'm simply going to turn all of them off except for one at a time. So this one is 2 times 1 minus sine theta. So this is what it looks like. It's called a cardioid. It's also a limacon. And then we'll turn this one on, also oriented in sine, but because of the plus, it's mostly above. And then we've got this one, and finally the last one. Okay. Let's talk about roses now. Roses are one of the more important polar curves that we work with. We often use roses to find arc length, or we'll use it to find the area of the petal of the rose. They form petals in their more simple forms. They do have more complicated forms where they're not exactly petals anymore, but it still resembles a flower, so it's still called a rose. Now, these have an equation a cosine of b theta or a sine of b theta, where a and b obviously can't be 0 because then it would just be a degenerate equation. Now, when b is an odd number, we get exactly b petals. And when b is an even number, we get twice that number of petals. So let's take a look at some of these roses. Now, this is for a and b integer values. So right here, we've got one where n is even, and we've got 1, 2, 3, 4, 5, 6, 7, 8. All right, so this would have been 4 theta. right? Because it's an even number, you get double the number of petals. And this one has 3 petals, so this must have been a sine of 3 theta. Now, how do I know what A is? Well, of course, the maximum length here is on the 1, 2, 3, 4th concentric circle. So this must be 4 sine of 3 theta, all right? Now, they do have symmetry, but it's not always symmetry related to an axis. For example, this one does not have symmetry to the x-axis, the y-axis, but it does have symmetry to the pole. If you were to fold it twice, it would lay on top of itself. Now, this one has 4 petals, which is an even number. So the coefficient of the trig, or the coefficient of the angle, must be 2. So we have 2 sine of 2 theta. And the reason is this maximum distance here, if you measure out this way, that distance right there is going to be 2. So if we measure from here to here, that's going to be 2. And that distance over here is 2. And likewise, that's 2. And that is 2, right? And so we're getting angles where it's reaching that value. This is at pi over 4. This is going to be at 3 pi over 4, 5 pi over 4, and 7 pi over 4 when it's reaching its maximum. All right. Okay. Let's now take a look. I've got different ones here for you to look at. Notice on this one that when we change the coefficient from 2 to 4, that the petals get longer. The 4 determines the maximum length of the petal. So in this case, it's 4. In this case, it's 2. And the same thing happens when we look at them with sine. Sine off kilters them a little bit, and they go out into the quadrant instead of along the axes lines for all of them. All right, so this is 2 sine of 3 theta and 4 sine of 3 theta. And again, the length of the petal, the maximum length, is the coefficient value that you see right there. All right, and here is 2 cosine of 3 theta, 4 cosine of 3 theta. Right. And then we can take a look at some examples and we can go graph them. I'm not going to force you to figure out what they are. It would be great if you could, but you don't have to. This 2 plus 2 cosine of theta is a cardioid, though, because the 2's are the same, and it does have the limacon pattern. So this one is going to be a cardioid. And if we want to look at what it looks like, almost misspelled cardioid, we can go out here and we can click on it and we get the cardioid for that particular one. Now the next one down here, 7 plus 4 sine of theta, this is going to be a limacon. Oops, messed up my C with a squiggle on the bottom. So this is a limacon, and I can look at 7 divided by 4, which is between 2 and 1, which must mean that this one has a dimple in it. So let's go ahead and see if it does in fact have a dimple. So it should have a dimple, and there it is, right? And so we should probably write dimpled limacon, right? And this one right here, r equal to theta, I believe that's an Archimedean spiral. So let's take a look and see what it looks like. Archimedean spirals are easy to detect because the distance between the spirals is the same. The logarithmic ones, they get further and further apart. They're the ones like the Nautilus seashell. So this one is an Archimedean spiral. And this one is, well, to tell you the truth, I've forgotten. Is that a no, it's not a logarithmic spiral. Is it a circle? I'm not sure. Let's take a look. No, it's a rose, of course. I totally forgot about the rose. Not a circle. It's not been shifted. So this is a rose, and it's going to have 12 petals. Why 12 petals? Because the coefficient of theta is 6, so you get double since it's an even number, and the maximum length of the petals is going to be 4. All right, now this next one looks like a Limnus Gate, so we can graph this one as well. Plot it. And there is a Limnus Gate. This one happens to have x-axis symmetry, y-axis symmetry, and symmetry with respect to the pole. So it has all 3 types. So this is a Limnus Gate. Right. And let's now talk about roses that don't have integer values. So let's remind ourselves of what the equation for roses are. So the formula for roses are these right here. And we're going to copy these and then we're going to paste them down below. So when we're looking at these, let me paste this right here. So there's our formula for the rows. Now the roses we've been looking at, A and B, were integers. What if they're not integers? So in this case, what happens is we get either what's called a closed curve, or we end up with what's called a space filling curve, depending on what the coefficient of theta is. So when we're looking at the coefficient of theta and it's a rational number, but not an integer or an irrational number, then some weird things happen. If it's a rational number, but not an integer, so I'm talking about numbers like 2/3 or 9/2 or 5/2 or 6/5. All right, if it's a rational number that doesn't reduce to be an integer, and that's what the coefficient of theta is, we call that a closed curve. Now, what it does is it repeats the same pattern over and over again, forever and forever, but they aren't exactly petals. Instead, it resembles a different kind of a rose, all right? And when the coefficient of theta is irrational, it actually fills up the space and is called a space filling curve. So here's an example of one. This is one where we have a rational coefficient of theta. It doesn't matter what this one is. But when the coefficient of theta is a rational number that doesn't reduce to be an integer, like 2/3, we get this sort of rose shape right here. And hopefully this it still resembles a rose to you when you're looking at it. It does take longer to graph the full shape. So this will take us out to 6π to get the full rose. But if I continued to go past 6π, it would just continue to trace out exactly the same pattern on the rows. So it would trace this path again and again and again. And that's what we mean by a closed curve. Let's now take a look at a rose with a rational coefficient that actually terminates. So this one up here was a rational coefficient, but it's a repeating decimal. So 2/3 is a repeating decimal. It gives a rose of this shape that we see here. And now we're going to take a look at a rose that also has, again, a rational but not integer coefficient of theta, but 9 divided by 4 is a terminating decimal, right? That's 2.25. So it doesn't repeat. 2/3 is 0.66666 forever and ever and ever. What difference does it make in the graph? Well, it gives us petals like we had before, but they're overlapping. So they're not separated like they were when the coefficient of theta was an integer value. They're overlapping. These are actually, I think, quite beautiful. I like these quite a bit. All right, so we have that value right there. And notice that even though it looks solid there around the pole, that in fact those lines do not intersect until they get to the pole. That's the only place that they touch, right? Now, Desmos can have trouble graphing the ones with coefficients that are repeating decimals because it approximates when it does it. So sometimes it makes an error when it actually graphs the ones that have repeating decimals, particularly the ones that aren't the major ones like 2/3 and 1/3. It can, by mistake, produce what looks like a space-filling curve. They should still be closed curves. It should give you a definite pattern that should repeat over and over again, like this one right here. So it should continue to give you this pattern. It should not fill up the space. But sometimes Desmos messes up just because it's a repeating pattern and it's approximating, and so it graphs it incorrectly. Now let's take a look at what happens when the rows has an irrational coefficient. So to make it irrational, all we need to do is multiply or divide by an irrational number, like pi or e or the square root of 2 or square root of 3 or something like that. So I multiplied theta by pi over 2. And what we're going to do is we're going to watch down here on these images, and we're going to see what happens as the value of theta gets larger and larger. Now with a rational coefficient, it's a closed curve, which means it produces the same pattern over and over and over again. But with an irrational coefficient, it becomes what we call space filling. So this one goes from 0 to 12 pi, and you can see it right here. It's kind of stopped there and stopped there, but it does kind of resemble a flower. So it is still called a rose. And then this one here, you can tell it's more dense, right? There are more overlapping spirals in here. And this is going out to theta equal 24 pi. And in the next one, I doubled it again and I went out to 48 pi, and there's even more spirals and they're getting thicker in here, right? So you can tell it's taking up more of the space inside of this rose. Now let's double 48 pi and we get to 96 pi, and you can tell that it's getting even thicker in here. There's still white space, but there's much less of it than there was before. It's starting to fill the space. And then I doubled it again, or actually I went more than double. I actually made it 200 pi. So this is from 0 to 200 pi. Now there's still some white space. You can still see the white space in various places around this, but it is starting to fill the space. And this is what we mean by a space filling curve. The last one goes up to 300 pi. And at that point, even though there's probably still spaces, they don't show up anymore on Desmos because the lines are too wide. And so it looks like a solid dot. So this becomes what's called a space filling curve. And as you allow theta to go to infinity, it will completely fill the space and cover it up with a solid color. All right. There are other types of curves as well. I'm going to show you just a few just for fun. These are not ones that I expect you to be as familiar with as the limacons, the lemniscates, the circles, the roses, and the cardioids. We won't work very often with spirals, although we may work with spirals when we're trying to find arc length. We don't tend to find area because they're not closed shapes, right? So it's a little bit harder to find the area. All right, now this one is actually called a seesoid, and it looks kind of like a kid drawing a bird, but tilted sideways. And this is the equation 2 sine theta tangent of theta. And so it has this sort of equation right here. It's a seesoid. And then we have a hippopede, which we saw earlier. It was one of our examples when we were looking at symmetry. It's basically two circles side by side. And it produces this very symmetric graph, all right, that you see right here. So that's a hippopede. And then we have the Concoid of Nicomedes, which can be turned one of two directions. It's either a plus b secant of theta or a plus b cosecant of theta. So the cosecant of theta, the one that I have right here, is oriented sort of horizontally. You can see it has this sort of hill shape here. And then it comes down, it has this loop below the pole right here. And then these branches get closer and closer together as it moves further and further out, all right? And this is just graphing from 0 to 2 pi, all right? But remember that the cosecant value goes from negative infinity to, or not from negative, it goes from 1 to infinity and negative infinity to negative 1. So you know that these values are going forever, right? To the left and to the right. And then if you use secant of theta, you can get a vertically oriented one right here. This is 8 plus 3 secant of theta, and you can see that it's oriented vertically. Now the butterfly curve is a really fun curve to look at. And this is the butterfly curve, which does look like a butterfly. All right, so I gave the equation for it up here. If you want to try that on your graphing calculator in Desmos, this is the well-known butterfly curve. And then this one does not have a name, but I really like it, so I like to put it on here. It actually has interlocking spirals for the sides of a heart shape. And then below the cusp, it has another heart shape also with interlocking petals. All right, so this is a really fascinating polar graph. And here's the equation for it down here. You can see the equation. And I put a link into Desmos that you can go play with it yourself and see what happens. The fun thing about Desmos is as you enter this equation, you can see the effect on the graph and what makes it more and more like a heart shape. And you can actually see the shape taking shape. All right, now there are other more complicated polar curves that exist. This is an example of a polar curve. It's quite a complicated one. I did not give the equation for that or a link to that, but it is an image that exists out there on the internet. This one does as well. This is an annulus shape, a ring shape of interlocking spirals, which is kind of interesting. And this one is yet another interesting polar curve that you have right here down at the bottom. All right, it has a lot of symmetry to itself. I hope you've enjoyed learning about some of the more exotic polar graphs and that you understand better how to use symmetry and maxima and zeros to help you plot these graphs. In our next video, we're going to be taking a look at doing calculus with polar coordinates. And that means finding the area, say, of a petal of a rose or finding the arc length from one point to another on the curve. I hope you'll join me for that video.